so all of this simple harmonic motion can be expressed using a trig function. We're going to use cosine, okay? So xm is basically the amplitude. It's the maximum displacement that your object achieves, okay? Which should kind of make sense, right? Because cosine of theta, what's the biggest value cosine of theta can get? 1, right? And what's the smallest it can get? -1, right? So the idea is my amplitude is going to oscillate between a positive maximum value, smaller fractions of it, all the way down to a negative positive amplitude. I just said negative positive. Negative maximum amplitude. Does that make sense? All right. So this is my amplitude, and then you're just multiplying by a number between positive and -1. Cool? And then it's cyclical, right? I mean, if you graph sine or cosine, it does this, right? Okay? So here the position oscillates between a position of x, the m stands for max. That's why we use that, okay? So x max and negative x max with an angular frequency of omega, right? The omega tells you kind of what the frequency of the oscillation is measured in radians per second, okay? Cool. So this whole expression here, you guys, is called the phase of motion. Okay? Note that the object might not start at a position of 0 at time 0. Okay? And so this phi here, or phi if you prefer, is called the phase constant. And it basically, it's that thing that shifts your graph so that your time 0 corresponds with your position at that point. Follow? All right, so I think probably the easiest way for you guys to do this and for this to make some sense is to actually do an example. Okay? So that's exactly what we're going to do. All right, so over here I've got this mass hanging here. It's a mass of 0.2 kilograms. All right, excuse me. This spring has some spring constant. I don't happen to know what it is. All right, and I did a crap job and I kind of set it up so the bottom of the spring lines up here where the position is 0. Cool? All right, sitting down on the floor where you can't see, there's a motion detector. And in this little program, oh, darn it. Darn it, didn't save. All right, give me 1 second, you guys. I got to do something real fast. So don't have time for this today. All right, so collect data, clear all data, experiment, data. New calculated column, position, let's make that be blue. Thank you for your patience. Position minus 0.711. Insert, additional graph. Ugh. Acceleration, data, column options, acceleration, options, color, green, done. Page, auto arrange, good. All right, that's gonna have to do. Okay, so. Hopefully this will work. I did this really quickly. All right, so what I've got here, like I said, is just a mass at the end of a spring. I'm going to set it into simple harmonic motion. All right, and we're going to look at the graph and see if we can come up with this equation for this thing. Follow? All right, so here we go. so that's going. Let's gather some data for it. So I'm just going to go over here and hit collect. Oh, over here and hit collect. Oh, look at that. That's very satisfying. So let's auto scale these guys so we can get a better look at them. That works really well, doesn't it? Okay? So, darn it, this actually came out at time 0 being really close to the max. I'm going to do this one more time because to make a point, I want it to not be. You know what I mean? Like I want this to not be a perfect sine curve. So let's do it one more time. I'm just going to hit collect again. There we go, better. Okay.
That's going to be like
Okay, good? All right, so, where did I put my notes? All right, so this graph gives us a bunch of information, right? So first of all, by looking at the graph, I can kind of tell what my maximum position is, right? So it looks like, according to the graph, my x max is a little bit more than 0.1 meters, right? You guys agree? So I know I could use the graph to read it, but let's just for simplicity, let's call it 0.15 meters. Oh, no. Sorry. It's clearly not that high. How about 0.11? Cool? All right. What else can we get from this graph?
period.
Period. Can't we get the period? Right? Just by looking at how much time it takes to go from maximum to maximum, or from equilibrium to equilibrium, right? So let's do max to max. So if I go from maximum to maximum, oops. So it looks like this is what? Let's see, 2, 4, 6. So this is maybe what, 0.65 seconds. And this over here is what, 0.215 or 2.15 seconds? Something like that. Cool? So the difference between those is, why can't I math? 1.5 seconds, is that what that gives us?
Isn't that like 2.25?
Oh, 2.25, thank you. Man, I'm struggling today. 2.25 seconds, thank you. So our period then looks like it's about 1.6 seconds. Follow? Obviously, I'm being a little bit sloppy here just because I want to kind of move on. But are we good? All right, and you should theoretically be able to repeat that process, you know, by finding how much time elapses between here and here, or between here and here, and you should get somewhere in the neighborhood of 1.6 seconds. Good? Questions? Okay, so before we go on and start analyzing this, I guess I should point out a couple other things, and this will be more relevant later on. If you look at the graphs, at my maximum position, here, let me get this thing going again. At my maximum positions, both at the top and at the bottom, what's the velocity? 0, right? So let's take a look at our graph and see if that actually works. Maximum position, velocity 0. Minimum position, velocity 0. Good? All right, now, what, in one word, what's providing the acceleration? So the spring and the gravity force, though, right? Right? When should the force be maximized? Thinking about Hooke's law. At the max, right? Shouldn't there be, remember, your force is proportional to your stretch, right? So isn't the spring providing the most force at the maximum? Well, the maximum down here, right?
Yeah.
Okay? And at the top, it's providing the least force, so gravity is going to have the most impact. Okay? So shouldn't the most force also correspond to the most acceleration? Right? And those correspond to our maximums, right? So look. Maximum position, maximum acceleration, right? Maximum but negative, right? Same thing here. Minimum position, maximum acceleration. Cool? Yes.
Is that a position of 0 is the force of the spring or the force of gravity?
Yes. Do I agree with that? Well, let's look at our graph. So you're saying when the position is 0, does the force of the spring equal the force of gravity? Well, our acceleration is 0, which tells me the net force is 0. So I think so. Yeah, that makes sense. Follow?
Yeah.
Everybody good? All right, so these graphs tell us obviously a ton of information. All right, so let's go back to here and let's record some of the stuff we just decided on. So we just decided that our period was 1.6 seconds, right? Okay? Oh, well, I can, if I wanted to, I could use that to find my frequency. My frequency would be 1 cycle in 1.6 seconds, right? So 1.6 is 8/5, so 5/8, so that's 625 hertz. Good? All right, now, remember, we decided that we could express our simple harmonic motion using this. Our position at time t ought to be some maximum displacement times the cosine of our angular frequency times t, right, that's the variable, plus some phi that ensures that our time 0 corresponds to the position at that time. Okay, it's our shift, right? So, let's see. Oh, we found our x max, right? What did we decide x max was? I think we used 0.11 meters, didn't we? Cool? All right, so what else, which of these other variables can I find easily? We can find omega, right? Because remember, omega is, if you take one cycle and think of it as 2 pi radians, it's the number of radians per second, right? So, let's see. Omega is 2 pi radians divided by the period, right? To find out how many radians I complete per second. So 2 pi radians over 1.6 seconds gives us, did I by any chance when I did this the other day? Oh shoot, it's 1.55 seconds when I did it in my notes. 2 pi divided by 1.6, and it gives you 3.93 basically. And what are the units there, you guys? Radians per second, right? Follow? Okay, cool. So the only other thing we need to figure out is what phi is, right? Okay, what did we decide that was called? Phase constant? Yeah, so we need to find our phase constant, this phi. So, how can I find phi? Can't we just pick a point?
Yeah.
Pick any point, right, where you know the time and the position at that time, and solve for the missing thing, which is phi, right? So, let's pick this max. It really doesn't matter. You can pick any point you want, but arbitrarily, I'm going to pick this point. Okay? Ordinarily, I would say pick the point where your time is 0, but because of the way the motion detector works, I don't know the position at time 0, so I can't with this particular thing. For most like homework problems, that would be my recommendation, is choose t equals 0 and solve for phi. Make sense? Okay, so at this point, it looks like the time is 0.65 and the x max is 0.11. So here we go. So x of 0.65 seconds is 0.11 meters. So here we go. 0.11 equals x max, which is 0.11, times the cosine of omega, which is 3.93t plus phi. Oh, what did we, sorry, we decided what t was. T was, what did we say, 0.65? All right, did I lose anybody there? If you're confused, speak now. You guys are just gonna get, you guys just got married to that equation. No? Everybody's good? All right, so divide both sides by 0.11, and you get 1 equals the cosine of this mess, which means that this mess needs to be 0, right? Follow? Which means that phi needs to be negative whatever 3.93 times 0.65 is. So what's that give us? Times 0.65. So it gives you like 2.55, negative 2.55
Is 1/3 not 2?
radians. Good? So here we go. That means that this motion here can be described by the equation position at time t equals 0.11, because that's our maximum, times the cosine of omega, which was 3.93t, minus 5, which is 2.55. There you go. There's our equation for that motion. I'm going to move this so that it doesn't kill me when I poke my eye out on it. All right. Questions? All right.
Actually,
Yeah.
So can we use sine instead of cosine and have a different phase angle? Or
Yep, you could. You could do that for whatever reason. This is the accepted way to do it.
Okay.
I don't have a good reason why.
Okay.
It's just how it's done. And I'll be honest with you, if I ruled the world, I would use sine.
Mr. Hecker to roll the world.
Yeah, next time I will. All right, everybody good? Any problems? AJ, remind me to send Sobelak the thing. Okay, all right, so did we hit everything here? I guess that's it. Oh. Yeah, all right, I'm going to leave it at that. There is actually one thing that I'm oversimplifying, but I think it's going to be a non-issue. So, all right.
Now I want to know.
Okay, so if this is the equation for position, how do we find the velocity at any given instant? Take a derivative, right? Because remember, the velocity at time t is just dx dt, right? So if you take the derivative of this, remember the derivative of cosine is negative sine, and then you got to use the chain rule and take the derivative of omega t plus phi, so that pulls an omega out, and you get this. Do I need to run through how to take that derivative, or are we okay with that? Are you guys far enough in your calculus now that you are cool with how to do that? All right, and then taking one more derivative gets us the acceleration. Follow? All right, so here's the super cool thing about acceleration. This is where things kind of all come together. Check it out. What's that?
The beginning. It's the first equation.
Oh my glob, that's the same as this. Oh, holy shnikes. My acceleration is the same as x of t times negative omega squared, whatever your omega is. Right? Oh, look, this shows us if my acceleration is proportional to my displacement, then so is my force. Right? This is, oh, wait a minute. If I multiply both sides of this by m, then I get this equation. So F equals something times x. What should I call the something? k, right?
Why?
Why? Because F, remember, simple harmonic motion is defined as motion in which F equals negative kx, where your force is proportional to your x. Is that a genuine nod or a blank, I have no idea what the hell he just said, nod?
Like, did that equation come from the other one, or is...
What we just accomplished is we just proved that the graph we just looked at
Yeah.
is in fact simple harmonic motion.
Which one came first?
For us, this came second.
Okay.
Good?
So then they were like, let's just make this the value k.
I gotcha. Yeah. Yes. All right. Are we good or no? Frothy, you good over there?
Yeah.
All right.
What is it?
Oops, too far. Okay. So what we're gonna do then, you guys, is this. So we're gonna rename this negative, or well, not the negative, the m omega squared. We're gonna call that k. Cool? Any problems? Okay. So, what this allows us to do is it allows us to figure out the period. And my brain has just stopped for a second. How do we do that? Oh, right. Okay. So, is everybody good with this substitution? All right, so what we're doing is we're defining a new variable. We're saying, let's define k, this spring constant, although we'll see it doesn't always have to be a spring, okay? But let's take this constant and call m omega squared. We'll define that to be our constant. Good?
So, Mr.
Alright.
Becker,
Yeah.
you said that we use this to prove simple harmonic, that it is simple harmonic motion, but you just sort of took the equation for simple harmonic motion and plugged it in.
What do you mean?
Like, we just took the f of t equals kx and plugged it in. So I don't see how that's proven that.
Do you agree that this is a constant?
Yeah. Well, yes. All right, I see.
See what I'm saying?
Yeah.
All right, is everybody good, guys in back? So, I mean, the idea, so I guess here's the only jump we made. We had to make the assumption that this was, in fact, a cosine graph. Okay? And the period of a cosine graph is constant, which means that our angular frequency is constant, which means that m omega squared is constant. Follow?
Yeah.
Okay. All right, so here's what we're going to do then. So we now have two equations that have omega. We've got k equals m omega squared, and we have omega is 2 pi over t. Right? By definition? So doing a little bit of algebra, rearranging those guys and solving for t gives us this equation, which you may remember from last year maybe, but probably not. But last year we learned that the period of an oscillating spring is this mess. So this is where it comes from. This is why I didn't show you that last year when you were in honors. All right? Questions?
Yep.
Yes, questions, or yes, you understand?
No, I wasn't thinking about what I was actually responding. It's like one of those where somebody's like, "Oh, how are you?" I'm like, "Good," even if we haven't a terrible day.
Oh, gotcha.
I'm not.
I'm a big fan of, how's it going? Yes.
Oh yeah.
That's what, yeah, right?
Or like, how's it going? I'm still.
Right.
Asking for the food.
Yeah. All right, so is everybody good with this?
Every.
All right, so most of your homework is going to revolve around tinkering with these little k and omega equations and plugging them into these three guys up here. Good? All right. All right. I don't know if there's really anything to say about this graph here. What this is meant to represent is it's just showing you kind of how the motion works. So these are like snapshots, right? So it's saying if at time 0 your position is here, then as your time goes on, you know, your thing is going to get pulled back towards the center. Notice the direction of motion. I don't know. I don't have anything to say about this. I almost deleted this slide. I now wish I had, because now I feel like I'm standing here like a dummy. Let me point this out, I guess. Do you guys agree that you can, just by looking at the position graph, you can tell the direction of motion, you can tell whether it's speeding up or slowing down, you can, and therefore tell if the acceleration is positive or negative? Like, do you guys get all of that?
Yes.
Right? Like, here, let me clear all this ink out of here. Maybe. No, that'll work. Okay, so like at this point, for example, what's the slope of the line at that point?
0.
0, right? So that means that my velocity should be 0, right? We already established that, right? Okay? Should the acceleration be positive or negative? Well, let's think. We're going from a positive velocity to a negative velocity, right? Oh, my velocity is decreasing, so my acceleration should be negative at that point, right? No. Oh, it's a negative acceleration. Hooray. Cool? So let's pick an arbitrary point and make sure you guys kind of get what I'm showing. So at that point right there, position is positive or negative? Negative. Velocity, positive or negative? Negative. How do we know that? Slope downhill, right? Okay. And then my acceleration should be positive, right? Because it's getting less negative. It's moving towards positive, right? It turns out, for those of you who are calculus friendly, your inflection points occur right at your equilibrium points, because that's when your net force switches from being positive to negative. Cool? All right. Cool. So that's kind of what all this is about. All right. So looking at graphs, so these two graphs have a lot in common. What do you guys see? What's the only difference between these two graphs? Amplitudes. Your x max is different for those two graphs, right? On this one, you've got the same amplitude but different periods, and therefore different frequencies. Okay? These guys are the same, they're just going to have a different phase constant because it's shifted, right? The only difference is that the red one is the blue one shifted to the right. Good? Questions? Cool. All right. Now, so this is kind of the last thing we need to talk about, is this. The system can be thought of as an oscillation between potential energy and kinetic energy. All right? Over here, this one that I took down, this one's actually fairly complicated because we've got two types of potential energy to deal with, right? Because at the top, all of your energy is gravitational. At the bottom, all of your energy is elastic. And then at any point in between, it's a combination of elastic, gravitational, and kinetic, because it's moving anywhere except those two endpoints, right? Okay, so most of, but not all of, most of the problems that you'll be looking at will be a little bit more simple, where you really only need to worry about elastic and kinetic energy. Cool? All right, so let's look at these graphs and assume that that's what's going on. All right, so remember, potential energy, when you're talking about how do I want to say this? Yeah, let me leave it at that. So let's assume that these graphs model motion like this. So we learned that you can find the potential energy of a spring, 1/2 kx squared, right? We know our kinetic energy is 1/2 mv squared. So that means that our total energy, that E there stands for total energy if that's not obvious, our total energy can be found by either looking at a maximum position and saying that it's equal to the elastic potential energy there, right? Because you have no kinetic there, right? Or by looking at a maximum velocity Because the point of maximum velocity is when there's no EPE, right? Does that make sense or no? Okay? So your total energy is going to be equal to either your maximum kinetic energy or your maximum elastic potential energy. Follow? All right, so I want to do a thing. Let me pull out my notes here real quick and see what the thing is. Oh, one real quick note, you guys, unrelated to anything except that I'm thinking of it right now. Because we're measuring our angular frequency in radians, your calculator needs to be in radians. Okay, so watch out for that. Unless I give you an inclined plane, which may happen. All right. So here's what I'd like to do. Did I give you guys a blank page after this? I didn't. All right. So what I want to do is this. Let's draw the corresponding potential energy and kinetic energy graphs.
Majority of the next page is blank.
We're going to need that example. Thank you, Doug. Thank you. Okay, we'll have room here. All right, so let's do this. I'm going to draw two more graphs here in this space. All right, so the first graph is going to be potential energy as a function of time. Good? So, at what point is my potential energy going to be maximized? At what point is the potential energy maximized? Here, let me do this. At what point is the potential energy maximized? At the end points, right? But at both end points, both the positive max and the negative max, right? So, this is a positive max, this is a negative max. So this positive max has to correspond to a positive potential energy. And this one also does, right? You guys see what I did there? When is the potential energy zero? When is potential energy zero?
When it's on the axis.
If x is zero, right? So when it's on the axis. So here and here. So if you follow those down, here and here. Oh, and I missed another max, right? Oh, failed. All right, you guys kind of see what I did there or no? All right, cool. So here's my potential energy graph. This one, why am I unhappy with this? Oh, I just did a rotten job drawing it is all. So here. Does that make sense? Make sense?
Yeah.
All right, now let's do kinetic energy. So which of these graphs should I look at to do the kinetic energy? The velocity one, right? So when is my kinetic energy graph going to be maximized? When the velocity is maximized, right? Or minimized, right? Because of the v squared, right? So kinetic energy as a function of time. So let's see, my kinetic energy began at 0. So at these 3 points, the velocity is 0, my kinetic energy is going to be 0. So 0, 0, 0. Oh, dang it. Sorry, guys. Am I making any sense or no?
Yeah.
Are we good?
Yes.
All right. And then, let's see. Maximum kinetic energy occurs at these two green dots, right? So here and here. And so here's my kinetic energy graph.
Mr. Hacker,
I'm a little
shouldn't the lower dot on the potential energy line up with the maximum on K?
Did I do it wrong? Let's see. Sorry, let's see. So green dots. Oh, no, green dots, thank you. Shoot. Green dots. Green dots, there we go. Better? Thank you. All right, how are we doing?
Good.
All right, I didn't graph it for one awesomeness point. What's that look like?
Straight, yeah. There's no real consistency.
Right? And do you guys then agree that this max should equal this max, should equal this TE?
Yeah. Or any 2 points at the same time, right?
Or the sum of any 2 points at the same time, exactly so. Cool? Is that a question, Mom? You sure? I didn't have time for the extra syllable, sorry.
No, it's
I'll get you later. All right. Problems, you guys? All right, so let's do this then. Tomorrow your deal is to study for the test, yes?
Yes.
Yeah.
For Thursday, try it. Okay? Just this and... So the reason I put it on here twice is because if you read question E, it says there are 2 ways to do part D. Okay? So pick one of the ways and do it, and then on the other page try doing it the other way. Just part D. Good? Questions? Okay. I'm around in the morning tomorrow. You guys have dibs on me.
Let's say I have one left of those videos. I really want to know. Do I need to?
What am I doing? What am I doing? Oh, I'm emailing. What's her face? Compose. Sobolak. And Kavera. AJR. I have AJ Riser.
So basically,
3rd hour.
is an exchange student over the summer in and she's looking to stay with and she has this great grandmother named La Katrina. La Katrina's a way to say something vegetable back in the 1900s. And she doesn't know it, but La Katrina is like, we don't really
But there's this guy, like, following her around, he's like, dressed in black, like, men in black, and Tracker.
What are you saying?
we're show we're watching in Spanish.
Oh!
Yeah, it's a drama.
Didn't realize you were talking about a show. All I heard was there's a guy in black following me around.
No, yeah,
And
it's not
so,
real.
there's this guy following her around, and he's
Following
like,
her.
Katrina, like, he has, like, a picture, like, a picture that she has of her, like, great-grandmother, but he has it too, and then, like, she gets this fax at the house that she's staying at, and it's like, Cuidado, and it's got, like, the picture, and it's like,
Also,
oh,
there's a
no.
love triangle. The girl that lives in we're from LA.
So, is there like tennis finals?
I don't think so, but, like, if she asks you a question, you don't really want to be like, no. Because it's useful. Sorry. I don't know what she's going to do.
I want to throw this at somebody really bad.
I think you could do that.
Like
So basically just waste time until the...
because Profe, like, she was like telling me, and at least I'm pretty sure that's what she was saying. I was kind of going but like, she was like, oh yeah, if you want to like talk to like the two in like the next hour and like work with them like do, like a Google Doc on like stuff, and then you can like actually do the final. The so far, where one one group does it, then the next group continues, and they have to continue with whatever the group before did. So,
Yeah, but they started selling. Remember, a few weeks ago they had. I'm just.
have a good day.
Hey, how you doing?
Good. I was wondering if you could copy down the data from the lab that was turned in on Friday.
Copy down the data from the lab that was turned in on Friday.
I was in a lab group with Abby, and we didn't finish the last test. And so I was supposed to get a text with the rest of the, like,
What lab was due Friday? Oh, the conservation of momentum one. Gotcha. Who are you working with?
with Abby Nesson.
How much of the data did you get on day one?
Um,
Did you do some of the lab with them or no?
I did. So
Okay.
I think we finished, like, we messed up on something halfway through, and then yes, I did up to trial 4
Okay.
out of the 7.
I gotcha. So let's do this. When you come back, so today's just a work day. Oh no, it's not, because we're doing a lab. Damn it. I would like you to.
Because I could come in.
Do you understand how those other trials? How are those last 3 trials different? Do you remember? Take a look at the lab and
Yeah.
tell me how they're different.
Oh, so they're like one or the other. So they're like 1 through 4. It's like completely inelastic. But then 5 through 7, it could be one or the other.
Gotcha. Okay. Yes, I'm happy. Yes. So if that were. Who'd you work with again?
Abby and Dustin.
Abby and Dustin. You said that, and I processed Hannah and
Yeah.
Abby. We're good. Yeah.
Are you feeling well?
Oh yeah, I'm good. Yeah, just processing. Hey,
Do you have time to talk about your Google issue?
I do. Yeah, let me finish this email and then yes. Don't go away though.
No, I came and saw you, but then you were out of the office, and then
I gotcha.
I guess I hit on the help desk.
Right.
But then they closed the ticket out, so I thought you were good to go.
I thought I was too, and then it happened again.
So this morning,
Good?
Yes, I am. And then, yeah. Sorry about that.
You're okay. Sorry, 2 more seconds. Thanks, Anthony.
You're good.
Is Josh coming back for his, second?
I don't know the answer to that. He probably forgot it. Do you see him next hour? Oh, no, because that's 5th hour.
Is that's Jeff?
Yes.
Yes, okay, I'll just tell him. You played a prank on him about us, and I don't think he's ever forgiven you. Oops. Alright.
Okay.
I sent you an email. So this morning we had a network
Right.
disruption.
Yeah,
So that's from RISA.
right.
So
And
that's my reasoning today. I think you're having the issue is there's an internet connectivity issue.
okay,
Because it sounds like when you're getting the off snap is it's not loading properly.
correct. Yes. So, but it's been happening a ton. Like it happened yesterday.
And it's happening the same thing like when you use FileStream,
It's always through Google Drive.
the web.
Or through Google Chrome, I'm sorry.
Through Chrome.
Through Chrome. So just out of curiosity, I guess it was Corey asked me the same thing. So you guys are telling me that I can open files straight through FileStream. Doesn't it just open it in Chrome though?
No. That's the beauty of FileStream.
So like, let's see, honors.
I'm going to go on a limb here and say sometimes you're a pretty heavy user, the computer might be overloaded because it's only a 32-bit OS, which would be eliminated next year with Windows 10. It's going to be a 64-bit OS because it can utilize all the resources of that computer.
Okay. Yeah, I just opened it in Chrome. I just opened up a
It's
file.
doc,
Right, those are the only types of files that
so you don't have any Word documents or anything.
I've switched, before you gave me FileStream, I started converting everything over to Google Docs.
Mhm.
So the FileStream is kind of a moot point for me at this point.
Gotcha.
Know what I mean?
Mhm. So, if you want, we could try. I could dump Windows 10 on your computer, and you can see how that will do for you. Yeah, everything seems to be working okay, but it's another thing if you want to test it out. So I
How,
could try a different port on the switch and see if that would cause any stop the disruption.
how is Windows 10 different?
Oh, it's really different.
Is that, let me see,
I have about 10 people on it right now. They seem to be having good results.
would this be running 10?
Is it a Surface?
Yeah.
Yep.
Okay, that's fine then. We'll use it on this all the time.
Do you have any special software on this computer? I don't. You just
No.
use Logger Pro, right?
Yeah, I was about to say, other than Logger Pro, it's all pretty standard.
And everything else should work because there's all. If you want to try that, I can put it on after school for you. Or now it's whatever time you want. It's about a 45-minute process. And then if you want to put it back, I can put it back anytime as well.
Oh, really? Okay. Why don't we do it after school today? I'm out of the building anyway at a meeting
Sure
at North.
Okay.
Is that all right?
Yeah.
Great.
And
Cool.
then
I'll make sure I clean off my.
just shut it down and I'll take care of it.
Okay.
But if
Great.
you have any issues with it, let me know immediately and I can dump it back to Windows 7 for you.
Okay.
I put Matt McGuire, not his computer in his room, but I got him in the maker space.
Okay.
So that seems to be working well for him. I got Courtney on in the library, Peter Palin, Adams upstairs.
Okay. Great.
I'm just trying to think of people off the top of my head. Lisa Klein,
Okay.
Amanda Moon. So I got a pretty
Okay.
diverse set of.
And people are happy with it?
Seems to be going okay.
Great.
Steve Garrisey's on it.
Okay.
It's a little different, but it's coming next year regardless. So
Yeah.
I want to
Just as
put it
soon
in the
as you
classroom anyway to see if it works, and if there's any issues, we can get them ironed out before September comes around.
Okay. Yeah, and I mean more and more, like, so my knee-jerk reaction was, well, I really like that this allows you to access recent documents, and that's kind of a pain on 10.
Mhm.
But since I'm not using Docs, like Microsoft Docs anymore, it doesn't matter.
Yep.
So Yes, please. Great.
Okay.
Great.
We'll give it a whirl for you.
The only other thing I can think of that might maybe be an issue is that I have two Google accounts. I have my personal one and my work one, and I don't, maybe those are conflicting.
I would try signing out of your personal account on Chrome, and then just use it in like an incognito window or something.
Or in Internet Explorer. That's what I do. I have
Oh,
my
gotcha.
Internet Explorer is like my school account.
I almost never open my personal one though. So, like, I mean, today I haven't opened it. And it's still,
If you have it on Chrome, I would just sign out and remove it from the computer. Just, you can still use it, like clearly, if you make like a new incognito window, sign in for it, and see if that makes a difference, because Chrome is resource heavy, and like I said, with the 32-bit OS, you can't use all the memory that we have in those computers and all the
Gotcha.
processing speed. So
Okay.
that might be another issue, because I know you're a very heavy Google user,
Mhm.
which, with this, hopefully with the new operating system and the 64-bit OS, more memory, everything can be utilized with
Gotcha.
those resources. It'll alleviate, get rid of those problems, so.
Okay.
That's my next step in troubleshooting this, because no one else is having the issues with it.
right, yeah.
So I could try a different port on the switch as well.
Okay, yeah, I mean, you know better than I do, so I guess, I mean, let's do those two things. I mean, I guess try the switch or the different port or whatever you
Different port
said.
on the switch, just in case there was an issue with the one.
And try 10, and let's see if that helps.
If it doesn't and you want to go back, you just let me know and boom, I'll put it back for you.
Okay, well, if that doesn't help, then I'll try logging out of, with my personal account.
Okay.
Is that cool?
Yeah.
Okay,
We'll go from there.
right on. Sounds good. Are you set? Are you just waiting on? Oh, okay.
Yeah, that was-
Cool. Sorry to keep you waiting.
No worries. And I texted Doug. I don't have any thoughts for them, so I don't know like where he is right now.
That's fine. No big deal.
All right.
All right, thanks, and thank you.
Hey, no problem. I want to make sure you're good to go, so that's just, I understand that's not a fun thing when you're trying to get something and it crashes on you.
Right.
But if you hit refresh, does it load up?
Nope, I gotta restart the computer.
That's really weird. Okay.
Yeah.
That's our next step, so we're gonna get you on the 64-bit OS. I think that'll alleviate your problems. I did that to Steve Garrissey when I had I used to have a Windows 7 64-bit build, and then we had problems with it. But he had a Windows 7 64-bit build, and that got rid of his problems with it.
Okay.
So the thing the 64-bit OS is really gonna
Help out. Okay.
Do you use Class Manager though? Okay.
Well, not entirely true. I do use it. That's where Logger Pro is.
I can make a shortcut to your desktop for Logger Pro, so you can get it.
Okay, great.
I'll make sure you have it.
That would be good.
Because Class Manager is going away, unfortunately. That is
Yeah.
a 20-year-old program that was
I
coded
know.
by somebody that used to work here.
Right.
So you can't even get a replacement for it.
Right. Yeah.
So I will make a shortcut to Logger Pro.
So will it then be just installed on each of these computers individually next year? Is that the deal?
Yep, you tell me
Yeah.
the computers you need it on, and it just makes a shortcut. It pushes it out to, to the desktop.
Okay.
Double click it instead.
Great. Okay, cool.
It works.
So then I
made
can
sure
just.
that was one of the first things to
Right.
know, because I know
So
that's-
I can share, so if I have Logger Pro files, I can put them in my Google Drive, share them with the students, and the students can open it that way.
Correct. But,
Dynamite.
so it's not going to be on the computers. You can't assign it to certain students anymore. You have to tell me the computer names, and I can dump it on there. So you
That's
can't like go to the lab and open it up. That was the
That's
confusing
fine.
thing with the Class Manager. But so the computers you need it on, it's not a problem.
Okay, awesome. Thank you very much.
We'll touch base soon.
All right, sounds good. I appreciate your help.
Hey, no problem.
I'm still recording. If you're listening, hi.